Germany, mid to late 1800s. Life in Germany was marked by industrial and social revolutions, characterized by wealth and more freedoms gained through revolution. The average person's lifestyle improved. However, for one German mathematician named Bernard Riemann, life would be difficult and short, but in that time, revolutionary. In the spring of 1849, Riemann returned to Göttingen to study for a PhD under Gauss. In 1851, Riemann got his doctorate with a thesis on the theory of complex functions. And at the age of 27 in 1854, Riemann completed his professional thesis and delivered his habilitation lecture entitled On the Hypothesis Underlying Geometry. And it became one of the most remarkable, far-sighted lectures in the history of mathematics. And it would be the work of Riemann and those who advanced his work that would be brought to the attention of Albert Einstein by his friend and geometer Marcel Grossmann in the formulation of the theory of general relativity. It would be the tools developed by people like Elwin Bruno Christoffel and later generalized by Gregorio Ricci Curbastro and his student Tullio Levi-Civita in the absolute differential calculus, also known as the Ricci calculus, but today is mostly known as Tensor calculus. Figure It Out presents Tensor Calculus, the secret language of curved spaces. In math, a tensor is an algebraic object that describes a multilinear relationship between sets of algebraic objects related to a vector space. Tensors are defined independent of any basis. The concept of a tensor is what enabled an alternative formulation of the intrinsic differential geometry on a manifold in the form of the Riemann curvature tensor. In flat Euclidean spaces like Rn, the ordinary derivative is sufficient to describe an object's change with respect to a set of coordinates. However, on a curved space, the ordinary derivative does not account for the curvature inherent to the geometric structure of the space, which is essential for making sense of how vectors and tensors change as they move along a manifold. In curved spaces, coordinates are not globally uniform, and vectors at different points may not align in a way that makes sense for any kind of simple subtraction. Therefore, the covariant derivative enables us to compare vectors at different points using a method that accounts for curvature. This will be discussed more later. Transformation rules are the key to understanding tensors. In our last video, we covered how to go through the transformation rules for contravariant and covariant tensors, here demonstrating the transformation rule from one coordinate system to another, the unbarred to the barred or vice versa. And for covariant tensors, co below, we see this transformation rule. And for tensors, an inner product such as this is invariant, or is a scalar, in either coordinate system. For a rank 2 tensor, either contravariant or covariant here, the following transformation rules apply. And we can also use this to create a mixed tensor of rank 2. So getting a grasp on these transformation rules is essential to understanding how to work with tensors, especially in tensor calculus. And we can create any size tensor here and use a multidimensional chain rule to work out the details. And for our metric tensor, it transforms under the following rules here. So, now using these transformation rules, we can now talk about deriving an equation for something called the covariant derivative. But before we go there, the next order of business is to define something called the Christoffel symbols, the first step in our journey to tensor calculus. Now, tensor calculus, otherwise sometimes referred to as the Ricci calculus, we start with the idea of considering the following invariant. Let's take a scalar function in the barred coordinate system equal to the same scalar function in the unbarred system. Now, differentiating both sides with respect to the coordinate x bar I, we obtain the following derivative. Now, we see here that through the differentiation process, one of these terms right here are the components of a first rank tensor. That is a covariant tensor. So what we just did is we differentiated a scalar and produced a vector. A rank 0 to rank 1 transformation. A natural question would be to ask what happens if we extend this process to obtain a tensor of rank 2 from a tensor of rank 1. You might recall the transformation rule for a contravariant rank 1 tensor is as follows. And if we differentiate with respect to some x alpha, we get the following equation. Now, carefully applying the partial derivatives here, we wind up seeing that there's a second term generated here. This second term has implication. It means that the following quantity here does not form the components of a tensor. So this is where we begin to start to formulate our idea as what a covariant derivative should be. We need to develop a scheme for a new type of derivative, a new kind of derivative known as the covariant derivative. In fact, we need a covariant derivative to be one that enables us to obtain tensors from the differentiation of other tensors. And we're going to do that by expressing the second term of that differentiation with respect to what are known as the Christoffel symbols. And in fact, the process for developing such a scheme is the chief aim of tensor calculus. Let's explore this idea a little further. So let's discuss the Christoffel symbols. And there are two kinds, the first and second kind. A little notation here will be introduced. Here we have a Christoffel symbol of the first kind. And for some who are familiar a little bit with tensors, this expression might look familiar to you. The Christoffel symbol of the second kind is the one you'll see us use more frequently in this video, and it's defined here. And one can see that it's completely definable in terms of the metric. So from these definitions, one can see that the symbols are symmetric in the indices I and j. And that gives us a sense of something called the torsion-free property. That is the symmetric ability to interchange the indices I and j. And we'll expand on this a little more. So we're going to define something called the torsion tensor. And it's the difference of the two Christoffel symbols with their I and j indices swapped. For our purposes, torsion-free means that this difference is equal to 0, meaning that there is no torsion. The Christoffel symbols, known as the coefficient of connection, the connection coefficients, they provide a connection between tangent spaces. And in order for this to be smooth and continuous, we require a torsion-free property. So the connection that we are about to define here is known as the Levi-Civita connection, named after Tullio Levi-Civita. And this is the definition of a covariant derivative that is both torsion-free, as well as something being called metric compatible. It's compatible with our metric. Now, this is a unique connection, this Levi-Civita connection, and it is guaranteed by the fundamental theorem of Riemannian geometry, or Riemannian manifolds. One can think of metric compatibility as a form of preservation of the product rule, something that keeps angles preserved or unchanged through a process called parallel transport. Now, one should first examine how the Christoffel symbols transform under a change of coordinates. Again, how they would look in the barred and unbarred system with relation to each other. So, one can define the Christoffel symbol of the first kind in the barred system here using the indices LMN in the barred system. And by the definition of the Christoffel symbol of the first kind, we then have to calculate the quantities of the barred metric tensor quantities so that we can differentiate them. And thus, if we differentiate one of these quantities with respect to a coordinate x bar n, we will get the following equation, carefully distributing the derivative, the partial derivative, to each of the quantities in this expression. We get a rather lengthy expression. But since the indices on the metric tensor are symmetric, that is, that we can swap the I and j indices, we can actually rewrite this equation simply by doing just that. Swapping the I and j indices allows us to rewrite this particular derivative in this form. And this here is a more preferable form for the derivative. Now, having the derivative of this metric tensor quantity, we can now take the indices, the L, M, and N indices in this expression, and we can generate two more equations by permuting the indices, cyclically permuting them in the following way here. Okay, so let's take a look at what that will entail. I'm going to write out this expression using the permuted indices, first here. And although it may take a few moments to write out the indices explicitly, doing so really gives you a sense of how the indices are placed and to get the transformation rules down pat. So I recommend to those viewing, don't skip on this part. Write out all the indices and get a feel for how the terms and the expressions play out. So we can express the transformation rule for the Christoffel symbol of the first kind here using this expression. And this would demonstrate to us that this particular symbol would transform as a tensor only if that second term vanishes to zero. In other words, the second derivative term there. So when the second term actually vanishes, there's a name for this. The transformation is called an affine connection, or an affine transformation. Now, if we want to get a transformation for the Christoffel symbol of the second kind, which is the one that we'll be using more, we just simply use the connection between the first and second kind. And now that we have the transformation rule here for the metric, or the inverse metric, we can then play out the rules as follows. Multiplying both sides of the equation that we demonstrated for the barred system of the Christoffel symbol of the first kind by the barred inverse metric, we get the following expression for the barred Christoffel symbol of the second kind. Okay, now what we're going to do is we're going to take the inner product of this with the partial derivative dx upper r dx bar p. And what will that yield? Well, let's play it out here in the equations. Carefully multiplying through, alright, and now that we have that written out, we can make the following note. This second derivative term can be expressed as follows in terms of the Christoffel symbols. So this is a very useful formula that we can now substitute back into our differentiation formula. So now we have our transformation laws, and we want to write out our covariant derivative with our imposed conditions. So dA upper beta by dx lower alpha, expressed as this, determined before, can now be rewritten with that second derivative term expressed in terms of the Christoffel symbols. And we make a few appropriate changes of indices to match up with our derivatives. So now we can write our formula here as substituting in and again, this is a good exercise to play around with the terms and their indices, and once in a while switching them up so that you know how to appropriately change them up. And our covariant derivative is taking shape. And this equation now can be reduced down to the following. This is our covariant derivative. Alright, next. What to do with this covariant derivative? Well, we're going to talk a little bit about changing the notation just a little bit here. So you may see that the tensor notation for the covariant derivative might use this comma notation to indicate the differentiation. There are definitely some other notations used for the covariant derivative, some involving the del or nabla operator, and we'll discuss some of that later on. And this demonstrates that the covariant derivative has the same form as the basic transformation law for the components of a tensor, a mixed tensor of rank 2. The covariant derivative of the covariant vector, contravariant vector. And similarly, the derivative of the covariant tensor. So there's a covariant derivative of the contravariant tensor that we just looked at, and this is the covariant derivative of a covariant tensor, like a covector. And we see a simple change in sign in the covariant derivative formula for such a covariant tensor. And the covariant derivative of a scalar is the one that we would naturally partially derivative that we would expect. So now we're well equipped to discuss the Riemann curvature tensor. Sometimes it's also referred to as the Riemann-Christoffel curvature tensor due to Christoffel's reformulation of Riemann's tensor using his symbols. So here, if we have the covariant derivative of alpha with respect to beta, then we can discuss the second derivative, the second covariant derivative with respect to gamma. And we get this formulation. So we'll expand it out just to see how this plays out. And this particular derivative is important because we're going to see how it is used after we permute its indices to develop the Riemann curvature tensor. Something similar I covered in a previous video. So we get this derivative here, and swapping out indices beta and gamma yields the following equation. And once we do this, we subtract the difference of these two. We get the following result for the Riemann curvature tensor. It has 3 lower indices and 1 upper index. And it is defined completely in terms of the Christoffel symbols and their derivatives. This is considered a 4th rank mixed tensor. And this describes the curvature in any particular given dimensions on a manifold, a Riemannian manifold, a set defined with a metric. Now, the particular curvature tensor you may see for the Riemannian curvature tensor is one with a lowered index. And of course, that's obtained by use of the inner product of the fundamental metric tensor and the Riemannian curvature tensor, as follows. Now, there is also a Ricci tensor, which is formed with the Christoffel tensor by contracting a particular index of the Riemann-Christoffel tensor, and it produces a tensor with two lower indices here, and is defined using the Riemann curvature tensor with a set of indices summed over, a contraction of the indices. The Riemann curvature tensor calculates how volumes change as they move along something called geodesic paths. And we can also define something called the Ricci scalar through this particular inner product. And you'll notice that it sums over both indices. The tensors we just defined are key in defining the Einstein tensor, which is essential in the equations for general relativity. And that's this set of equations here. The lambda in this particular expression is the cosmological constant, where the tensor T sub mu nu is the stress energy momentum tensor, describing the energy content that is in the gravitational field, which can be geometrically described using the Einstein tensor, and g here is the gravitational constant, c is the speed of light. In fact, one of the first solutions to Einstein's field equations came from a man named Schwarzschild, and his solutions began the predictions of black holes, something that Einstein didn't really believe existed. But since then, other metrics have been produced, like those for rotating black holes called the Kerr metric, and a metric that actually describes the entire universe itself. So anyone who's studied vector calculus might be familiar with the Del or Nabla operator. And so let's just make some connections here. The gradient of a scalar field is given by this partial derivative, and the divergence can be defined in tensor form in this following way. The divergence producing a scalar. The curl can be defined in this way, and the Laplacian operator in this way. It's also worth noting that in special relativity, something called the Minkowski metric, a four-dimensionally flat spacetime metric, is used here. And one of the fundamental things that really inspired Einstein to take up general relativity was Maxwell and his equations for electromagnetism, given here using the Del operator. And one can define the tensor for the electromagnetic field, given here the EM field is an antisymmetric tensor. Finally, let lambda be a curve on a surface. Then the equation of a geodesic curve, or the straightest possible path, is given by this equation, known as the geodesic equation. So here's a problem for you to check out. something for you to figure out. Calculate the metric tensor, the line element ds squared, the Christoffel symbols, and the solutions to the geodesic equation for paths given in spherical coordinates. And your spherical coordinates are given here, where here we use phi as the azimuth angle and theta as the polar angle. Pause the video now if you'd like to figure it out. Alright, so we begin with our solution here, where x, y, and z are our Cartesian or new coordinates, or we'll call them the barred coordinates, and r, theta, and phi are our old spherical coordinates, the unbarred system. So defining our metric here as the product of the basis vectors, we can define our derivatives in terms of the different coordinates and their directions. So taking a few moments to calculate all these derivatives, we get all the derivatives in terms of dr, we get all our derivatives in terms of d theta, we get all our derivatives in terms of d phi. And for those of you familiar with the Jacobian of our matrix, a matrix that is made up of all of these different elements, the Jacobian cannot be equal to 0. Now that we have all of these derivatives explicitly written out, we are interested in calculating the metric coefficients, in which case the I and j coordinates are matched. You see, in an orthogonal coordinate system, if I and j are not matched, then it's equal to 0 given by the Kronecker delta. But here, we have to calculate what we call the diagonal elements are of our metric tensor. And using our partial derivatives, we can calculate g11 to be 1, g22 to be r squared, and the g33 term, well, that works out to be r squared sine squared of theta. So now our metric tensor has all off-diagonal elements 0 and diagonal elements given here. And because this is a diagonal matrix with symmetric ij indices, finding the inverse metric is not terribly difficult either. Now let's calculate the line element ds squared. And in terms of r, theta, and phi, we get the following quantities. Explicitly writing them out, then we would want to expand out these terms and simplify the results. I'll spare you some of the details here. We get the following result, which can be expressed in terms of the metric tensor in polar coordinates. So this is our line element. The next step will be a little tedious, but we can get through it, and that is to calculate all of the Christoffel symbols using the metric tensor quantities. Alright, we're going to have to dig deep here. First, let's note what our metric tensor quantities look like here, and we'll define the Christoffel symbol formula also here so that we can utilize it to generate all the different terms of the Christoffel symbols of the second kind. Our metric tensor inverse is given here, where all the diagonal elements are just the reciprocals of our particular original metric tensor diagonal elements. And so the first element of our Christoffel symbols we'll calculate is the gamma RRR term. Now when we explicitly write this out, we begin to see that we can do a little bit of simplification. That is, for the inverse metric lambda alpha, it'll be 0 when those terms are not equal. So we need to think about making sure that we only calculate when the terms of the inverse metric indices are equal to each other. So for the RR term, we need the G upper RR inverse metric term, and that's going to be expanded out and give us actually 0. Generating all the Christoffel symbols does take some time, and it's worth the effort to go through it just to see all the calculations work themselves out. One realizes that many of the Christoffel symbols work out to be 0. And after we calculate all of these particular terms, we will group them together in a matrix. So here we get a non-zero term of negative r. Again, writing out the terms here exploits the fact that the inverse metric has to have upper indices that match, otherwise we get a value of 0. It's a very useful part to making a lot of the terms go to 0 in the Christoffel symbols. Here exploring the R5 phi term, we get negative r sine squared theta. So collecting them into a matrix, we'll call it the gamma R matrix. Here are the Christoffel symbols in the R direction. Next, we do the same sort of exercise for the upper index theta, and there will be 9 quantities to calculate, many of them being 0. And thus we're only interested in the terms that have the inverse metric upper theta theta in this particular sense. Again, just going through the terms here and seeing how everything here plays out. And once we finalize all the non-zero terms in our Christoffel symbols, we'll be able to use them to calculate the geodesic paths along the surface of a sphere. So collecting them together here, and doing the ones for the phi coordinate, we get these 3 matrices. These are the set of all the connection coefficients given by the Christoffel symbols of the second kind under the Levi-Civita connection in spherical coordinates. So the very last task here is to calculate, if we can, the solution to the geodesic equation, and thus find geodesic paths on a sphere, which here will keep the radius fixed. So considering a fixed radial distance, the non-zero terms of the Christoffel symbols will depend only on theta and phi. And those non-zero terms in terms of theta and phi are given here. And the geodesic path curve will satisfy the geodesic equation given here. So we consider the 2 different directions, the theta direction and the phi direction. We'll consider the phi path first. So that is, as we move in the azimuthal direction, we would get a path, call it lambda, in terms would be some constant a times phi, and therefore we can set up the derivatives as follows. And therefore the geodesic equation satisfied is here. Writing out the terms explicitly, and we have the Christoffel symbols to fill in there. Now, in the terms of the theta direction, we get this geodesic equation. And this particular geodesic equation is satisfied when the angle theta sub 0 is either 0, pi over 2, or pi. For 0 and pi, we get the north and south pole. For theta equals pi over 2, we get the equator, which is a great circle, a geodesic curve around the globe. And with that, I hope you enjoyed this video. Please hit that like, subscribe, and notification bell for more videos, and please stay tuned for the next one. Thanks for watching.